record this now. So let's just look at some common functional groups that we encounter a lot in organic chemistry. So somebody name a functional group which they like.
Hydroxides.
Alcohol.
Okay, alcohol, sure. Okay, so alcohols. Right. Okay, so there's basically how many different flavors of alcohols do we have? We've got primary, we've got secondary, we've got tertiary,
Tequila.
and we've got there's a fourth type of alcohol that's attached to a different functional group as well, which would be
vinyl.
The we've got the phenol. Okay, right. And tequila basically has got a lot of ethanol in it. Okay, so we've already basically discussed okay, so some of the reactions of alcohols, one of the common ones, of course, is basically oxidations, right? So we can oxidize secondary alcohols to ketones. We can oxidize primary alcohols to aldehydes or carboxylic acids. Can we oxidize a phenol?
No.
We have a vote for no.
I second a vote for no.
It turns out you can oxidize a phenol. It's really interesting. Oops, that's supposed to be a double bond there. Let me erase all this. You can oxidize a phenol to a quinone, and then these can actually be reduced to these guys. You can re-aromatize the ring. So phenols can be oxidized, and it's not something that we would have seen very often in organic too, but it is possible to oxidize these two. And it's interesting. It's not just, you don't just oxidize the one alcohol. You actually insert another alcohol into the to where this carbon is here. So it's an interesting reaction. In biology, in biochemistry, these sort of interconversions are relatively common, I think. Somebody who's in biochem back me up on that.
It looks familiar.
Like there's something called ubiquinone.
Ubiquitin?
Yeah, and I'm pretty sure it's got this sort of structure in it, and then it can be, there's, I'll have to look that up. I vaguely remember that. Okay, so alcohols, they can be oxidized, and tertiary alcohols are basically resistant to this because they've got, as I said before. What were some other reactions that we did with alcohols? So oxidizing agents. The most popular two, which we would have seen, would have been PCC, and the other one would have been Jones reagent. Jones would have taken a primary alcohol, Jones to the carboxylic acid. PCC would have stopped at the aldehyde if it was anhydrous, so if there was no water in there. And both of them would have oxidized a secondary alcohol to a ketone. Those are the two main oxidizing agents I think we would have seen before in organic 2. And people in organic 3, remind me, did we see any other ones last year? I'll take that as a no. Well, the fun part is the second assignment we'll do is got to do with oxidizing agents. So don't choose this and don't choose that. But there's like tons of them out there. Some of them quite interesting, and they've all got their specific things that they're good for. So there are some oxidizing agents that will specifically oxidize a secondary alcohol in the presence of a primary alcohol. So that's kind of fun. What other reactions did alcohols undergo besides oxidations?
Wouldn't we just use them like as a nucleophile?
Okay, so a nucleophile in what type of reaction? Like
an SN1 or SN2?
okay, so we could use them for substitution reactions. Okay. Right. So if we had, say, this guy, and we wanted to make this guy, what would we use here and what would we use here? So we want to convert the OH into, say, into a nucleophile. So we use something to actually deprotonate it. So sodium hydride, this would make, and then we would want to put the electrophile, which we're adding here, 2 carbons. So maybe 2 carbons and an iodine is the leaving group. And this would be an SN2 reaction. For SN1 reactions, what the kids did what everyone did in the lab yesterday at the school was this. They had HCl, and this made through a carbocation, and the leaving group was water, right? So alcohol gets protonated, water leaves as a neutral molecule, got a carbocation, chlorine comes in and reacts with it. The trouble with this sort of reaction is that HCl is going to react with a whole bunch of things. So that's one of the problems. The other thing is that, I guess that's the main one. So alcohols can be used to convert, the hydroxyl group can be converted. In this case, it's been converted into a leaving group. So that's one way of doing things. And over here, it's actually converted into being the actual nucleophile, or if it was doing an elimination reaction, a base. So yeah, those are 2 other reactions that alcohols do. What would be a third? Did we do anything else with alcohols?
Protect them like from reactions.
Right. So yeah, exactly. So and the protecting group. So alcohols have got an acidic proton, and we're going to see this quite a bit. So sometimes it's important to protect that as a protecting group. The ones that we used the most were silicon based. So this would be what we would call a silyl ether. So carbon, oxygen, silicon. So carbon, oxygen, carbon, that's an ether. And this one's a silyl ether. And then you could do chemistry elsewhere in the molecule, and then you could remove it with fluoride, because that was a good group to remove silicon, and you regenerate your alcohol. So there's a whole bunch of different silicon protecting groups. They typically just used a silyl chloride plus a amine to deprotonate the alcohol. How did we make alcohols? And not the fermenting type.
Substitution reactions with water.
Okay, and what would you start with there?
I'd like an alkene.
Okay, so there's a couple. Yeah, there's a couple ways. Right. So if you start with an alkene, let's start with this alkene. You can let's start with a different one. You can make an alcohol. There's two different ways you could do this, I suppose. This would be one, and this would be the other. So you're adding, technically you're adding water. Put that in brackets. H goes on one carbon, the hydroxyl group goes on the other. So this is actually an addition reaction. Substitution, if we had, say, I don't know, so I say an alkyl halide, and we could try to do a SN2 reaction on this. This would be like a substitution reaction. So you can make alcohols from alkenes with addition reactions. The reagents here weren't necessarily water specifically. They were, so this would have been the oxymercuration reaction. And this one would have been the hydroboration. Right. There was something specific about the hydroboration reaction when you did this. If you had, let's erase this. The H and the OH would add on the same side. That was a specific thing about the hydroboration reaction. The oxymercuration, the OH group went on the more substituted carbon. In the hydroboration, it went on the least substituted carbon. So that would have been what we would call this one would have been a Markovnikov. And this one would have been the anti-Markovnikov, because the OH group was on the least substituted carbon. So you could make alcohols from alkyl halides. You can make them from alkenes. You can also make alcohols from other places as well. Alcohols was a good one to start with because it's got lots of fun things in it. What was another way to make alcohols?
Wait, did you go over this?
Oxides?
Okay, sorry, I missed that.
Did you go over this at the start? You had like your carboxylic acid.
Right. Okay, so you could do reductions, right? So if you have, it's basically exactly the opposite of a oxidation. So carboxylic acid could be reduced with lithium aluminum hydride. We always have to add acid in the second step to protonate everything. So this would give a primary alcohol. Ketones would give secondary alcohols, and you could use sodium borohydride or lithium aluminum hydride. And then aldehydes would give primary alcohols. So the primary, secondary. So yes, you can reduce those functional groups. What did an ester do? If you had, say, this, what would it produce if you tried to reduce it?
Was it a primary alcohol?
Right. It was. So if you use lithium aluminum hydride, you would get a primary alcohol. And the way that this would work is, let's try to draw the little mechanism here just to remind everybody. So OMe. I'll just draw the hydride as a H minus. Electrons attack, electrons move up. And then we would have our tetrahedral intermediate, the negative charge. And this is unstable, so it falls apart. And it would give us an aldehyde plus the OMe minus. But aldehydes are even more reactive than esters. So the excess lithium aluminum hydride would immediately attack there and the electrons would go up. And you would have this as your, I'm missing a carbon. 1, 2, yeah, you'd have this. And this would hang out because you got 1, 2, 3 carbons, 1, 2, 3. This would hang out in this form until you added your H plus, and then it would get oxidized. It would get protonated. So you get your primary alcohol. So this is what would happen. You'd get a primary alcohol if you used lithium aluminum hydride. What would happen if you used sodium borohydride?
Wouldn't it just stop at the aldehyde?
Yeah, sodium borohydride doesn't actually reduce esters. Esters. It is a it's not strong enough. It's not a strong enough reducing agent. There are the odd example where it does reduce esters, but typically sodium borohydride is not strong enough to reduce an ester. So if you had, say, a molecule like this, if you put in sodium borohydride, you would only reduce the ketone. You wouldn't touch the ester. But bringing up you'd get the aldehyde. There is a reagent which does this, and certain years we talk about it in class, and certain years we don't. But if you ever have an ester and you want to reduce it to the aldehyde, the reagent to use is what we call dibol. If someone wants to reserve that, go for it. But that's a neat reagent, and that will stop at the aldehyde. Okay, so right, so you can use reducing agents to convert carboxylic acids, ketones, aldehydes, esters to alcohols. What happens if you want a tertiary alcohol? How do you make those? Because these are making primary, secondary, primary. How do you make a tertiary alcohol? You can make them from these same sort of reagents. So you can use these sort of starting materials, but it's a different reagent. Okay, so if you want to make a tertiary alcohol, you start with this. You can start with the same materials. Let's say we've got acetone. We could make this guy by, all we need to do is have a nucleophile, which is a phenyl group. So the first step is that we need some alcohol, we need some reagent, which is a nucleophilic source of phenyl. Here we had nucleophilic sources of H- to reduce these things. How do we make, let's erase this. How do we have carbon with the minus? What would be a way of making that? What would this negative charge be needed to be bonded to make that?
Wasn't that Grignard?
Right, Grignard reagent. So Grignard reagent. So you could have magnesium bromide. And so this bond is polarized in this fashion. So it's basically a source of carbon with the minus. So, and you make a Grignard, and I believe everyone in class actually made this very Grignard here by using the alkyl bromide and then using the magnesium in diethyl ether. Does everyone remember that reaction? You had a reflux condenser and you had your little metal in it, and you stirred it and the metal gradually bubbled, turned silvery, and then disappeared.
Yeah.
Okay, so yeah, so you could basically use any RMGBr here, and so if you've got an alkyl halide, you can typically make a Grignard out of it, and so all of tertiary alcohols can be made from ketones or esters, or those would be the two ones which would be used the most. You use a ketone like we've got here, or an ester would also work. So yeah, that's basically that. So one component could be made from an alkyl halide with some magnesium, and the other component is just your carbonyl group. So that's good. Okay, so I think when it comes to alcohols, that is basically a pretty good synopsis of everything we've done with alcohols. And it's interesting because it ties into a couple of other functional groups, right? It ties into all of the carbonyl compounds, ketones, esters, aldehydes, carboxylic acids, and it also ties into alkyl halides, because you can use alkyl halides to make tertiary ones through Grignard reagents, or as I think it was Joel at the start said, you could use it over here in substitution reactions to make some simple alcohols. Plus it ties in alkenes, because you can do like hydroborations, oxymercurations, even dihydroxylations to make alcohols from double bonds. So the alcohol functional group is a pathway to a bunch of other functional groups, and it's also it can be made from a bunch of other ones. So it's either a destination or a starting point. So it's a fun functional group for sure. Let's see here. What were some other functional groups that we played around with? Okay.
Ethers?
How about, let's talk about ketones and aldehydes. Or what was the one you were about to say?
I just said ethers, so.
Okay, so
close.
ethers are, there is a little bit we can do with ethers. Let's talk about them in a little while. Let's talk about aldehydes and ketones just for a second. So we've just seen that if you've got an aldehyde or a ketone, you can react these with H- to make alcohols. Or you can react it with, say, R- Grignards to make alcohols too. This one would be primary, this one would be secondary. What about if you reacted an aldehyde with an alcohol? What type of reaction what type of product did we get with that? Or even before we even go there, what happens if you react an aldehyde with water? It's actually they're actually in equilibrium. If you've got a little bit of acid catalyst there, boom. Do we remember what they did? So you've got a little bit of acid in there. It protonates the carboxylic acid. You've now generated a pretty electrophilic carbon here.
Is it like cauterized or something? I can't remember.
Right. So this, it isn't, so you actually make what we would call a diol. Well, this is an equilibrium. I should point that out here. This is what we would call a 1,1 diol, or a sometimes called a gem diol, because both OHs are on the same carbon, so it's geminal and they're brothers or sisters or whatever Gemini is, right? Twins, that's it. So, and it just so happens that for almost everything, this equilibrium lies on the side of the carbonyl compound. But if you do it with an alcohol, H plus, and you do it with an alcohol, R primed, and you remove water, because water is a byproduct of this reaction. You make a specific type of you generate a different functional group altogether. And basically, instead of having two OH groups here, it's the the alcohols basically attack the carbonyl twice, so to speak. The leaving group in the end is water. This type of functional group, anyone remember what it was called? Sugars have this, well, disaccharides have this functional group in them.
An acetyl.
Right, that's it. Acetal, right. So acetal. And monosaccharides, which are, they would have the hemiacetal. So like most sugars are either going to be the 6-membered sugar or the 5-membered sugar, which you would see in, if carbon, oxygen, H, that is the hemiacetal. And the carbon, oxygen, carbon would be the acetal. So it's a slightly different, we're gonna see these a little bit during the course of the term, I guess. Good, okay, let's see here. So we already talked about if you have a triple bond, you can make the cis or the trans alkene using or H2 and Lindlar. Double bonds themselves. We reacted to a double bond with Br2. What was the interesting thing about this reaction when we put bromines on each carbon? What was the specific thing that was important about it?
They were on opposite sides.
Right. They were on opposite sides. Okay. And why were they trans to one another? it was a specific reason why they were trans. Right. They are trans because of this guy or this intermediate right here. So this 3-membered ring, bromine plus 2 carbons, the bromonium ion, and so the bromide, which had to attack, has to come in from the opposite side because this is one side's blocked by that big bromine group. So, right. And so, yeah, the bromonium, this bromonium ion is, so if we have, my cat is just meowing like crazy. I hope you can't hear it. Oh gosh. Cats are funny. Okay, so if you've got a double bond with, and you're adding HBr, this was what we would call the, you would form a carbocation intermediate, which was the most stable. And the most stable carbocation has got the most number of substituents. And then the bromine would come in and attack. And you would get your final, product. The so that would be the rich get richer, right? If dollars equals protons, this carbon here's got 1 proton, this carbon's got none, the rich get richer, you'd end up with this type of product. In the case of the bromine reaction, you would have bromine here, and it could come in and react with that proton to form the bromonium faster than the bromide ion, which was floating around in the reaction, could. I used to say that you can touch your feet faster. Well, I used to be able to. I could touch my feet faster than anyone else could touch my feet, right? So if it's attached to you, you can, if you've got some flexibility, you can touch your feet faster than anything else. So this is why you'd form this bromonium ion faster than the bromide could come in and attack. So you would get the trans species there. And so there, if you on Moodle here, I've gone through all of the various functional groups, and I've tried to talk about some of the reactions that they do. Yeah, let's talk about, aromatic rings for a second, because there was a whole class of reactions where we would use an electrophile here, and we would get this. So electrophilic aromatic substitution. So for these reactions to take place, the electrophile needed to be stronger than for a typical isolated double bond, because you had to overcome the that aromatic ring and the stability of that aromatic ring. So You needed to use really, really, really strong electrophiles to get this to work. So one example would have been if you wanted to add, say, let's say we wanted to put a ketone here. Does anyone remember the two reagents that were sort of critical to putting a ketone there? So one of them was aluminum trichloride, and this was a Lewis acid. And it would react with whatever reagents here to form a intermediate like this, which we could draw a resonance structure for, which was actually, I guess I should draw it linear, so it would be linear. Do we remember what that reagent was that would leave, that could generate something like this type of species? We haven't seen this functional group yet. And the other intermediate, the other thing which would form in the course of this reaction is this. Starts with acid. So we would use this guy. So aluminum would complex with the chlorine, then the oxygen would boot it all out. You'd end up with a positively charged electrophile, a really strong electrophile. And then the way that all of these, I guess I could have drawn this mechanism here like this. If you've got this, ring attacks, these electrons go up. H. This has got a positive charge. And like chloride or the aluminum chloride, some Lewis base here. Let's do it like this. Grab that, re-aromatize the ring. You would have your product. And so there was a whole series of different electrophiles that would be used, and it typically required, it required a catalyst to activate the electrophile. So if you wanted to, say, brominate an aromatic ring here, bromine, you would use Br2, but you would use like iron tribromide to activate. These two would interact, form a complex with the iron, and that would polarize the bromine to allow the ring to attack. It would basically be a very similar, you'd form a pi complex, then you would re-aromatize the ring. So those were all the electrophilic aromatic substitution reactions. There was, you could add bromine, you could do a nitration. I think you guys all did this in the lab. Using a mixture of nitric acid and sulfuric acid. to make to put on a nitro group. Yeah, the nitration of something or other. I'm pretty sure that that's what we did last term in term 2, in organic 2. So there was a whole series of reactions with electrophiles. And I guess the last general class of reaction that we should talk about is if you've got, for example, so acid chloride, and now you've got an ester, or you could use an acid chloride and you can make an amide. These were all what we would call nucleophilic acyl substitution reactions. So you need some nucleophiles. So in this case here, it would be our friend the alcohol, and you would need some base, like some non-nucleophilic base, like triethylamine, pyridine, something like that. And in the case of, if you wanted to make an amide, you would just use the amine, whatever amine you were wanting. In this case, you could use an excess. Part of it is being the nucleophile and part of it to be the base, because you've got to remove, in the case of the alcohol, you have to remove the proton. And in the case of like NH3, you'd be removing one of them because there's only 2 of them left on the side. So that was the other major class of reaction that we would that we did in organic 2. So nucleophilic acyl substitution reactions. So these are we would do these if you've got, say, anytime you've got a carbonyl that has a leaving group here. So the leaving group could be a chloride, or it could be an OMe, like, so it could be a acid chloride or an ester, or even a carboxylic acid. You're just going to convert that OH group to a proper leaving group. So that was nucleophilic acyl substitution reactions. These are slightly different than ketones when we're reducing them. These would just be nucleophilic addition reactions. All of these reactions with the alkenes were basically electrophilic addition reactions, because bromide Br2 is a electrophile. These would be nucleophilic addition reactions because hydride's a nucleophile. These electrophilic aromatic substitution reactions, electrophile. And we're converting an H to an electrophile. So that's why it's a substitution. And here we've got a chlorine, and it's being converted to a OR. So it's basically, it's a substitution. And that was really the 3 main classes of reactions that we did in organic 2, I believe. So did anyone look at the review PDF on Moodle?
Looked at a few pages.
Okay, so basically take a look at some of the reactions. Like I basically tried to dig up everything I could think of from organic 1 and organic 2 to put on there. You certainly don't need to memorize all that sort of stuff. But just take a look at it. Just take a look at it and get sort of familiar with it all again. I mean, hopefully, I think there are little exercise at the start, looking at a molecule and figuring out where various, like what parts of the molecule were flat, which ones were linear, what's the electrophilic site there, what's the nuclear. I think that was probably, hopefully helpful. It seemed to me that a lot of people sort of remembered what was going on. So just take a look at some of these reactions. Like the mechanisms are going to come back to us slowly, but they will come back to us, because what the really interesting part about the whole premise of this class is that we're going to take some molecules that are very simple, and we're going to build really, really complex things from them. And we're going to learn the basic strategies that people have employed over time to do these types of reactions. And with some of the case studies we do, the fun thing about doing this sort of stuff, because who doesn't like to play with Lego, right? Because it is basically building blocks and all that sort of stuff. But there's more than one way to accomplish these things. So there's a whole lot of creativity involved, which makes it super fun, as far as I can say. But the point I guess I'm trying to say is that we just got to get familiar with some of the tools that we have in our toolbox. So that's basically the point of doing that. So so take a look at some of these reactions over the weekend. If you're going to watch the football game, just bring out your thing and take a look. Or if you're watching, I don't know, Cooking with the Stars or whatever people watch, because you certainly don't need to study it. Just take a look and just remind yourself of everything that you already know. So, and then I'll do a brief little overview of organic chemistry on Tuesday, and then we'll talk about the strategies of how to build stuff next Thursday, I guess. And also take a look at the Moodle thing for the first assignment, because I've put on there the Birch reduction, and it's basically, it's not perfect, and it's specifically not perfect for a reason. So you guys can do an assessment of it, and that's basically how the whole thing is going to work. So take a look at it. If you've got any questions, just email me. And I guess we could discuss that more fully next Tuesday. And before next Tuesday, I'll have all of the lab stuff, and I'll send out an email about that too. So. Does that sound good?
Yep.
Okay, excellent. So have a good day, everybody. And because I think it's basically 1:30 now. And I'll see you by Tuesday at the latest. You bet. Okay. Bye-bye, everybody.
All right.